developed these ultra precise atomic clocks. So we're going to learn more about those today. In a MEMS language, we know about clocks, we know about oscillators. We know that Q is important for stable references. So today, Shimon will talk about systems, optical clocks, where we're talking about Qs in the range of 10 to the 16, and now they're pushing that even a few orders of magnitudes beyond. So let's hear about how to make these ultra precise clocks using, atomic physics techniques. So super excited to have you.
Okay, so thanks a lot. Thanks a lot, Alp, for the very kind introduction and the sort of historical perspective. It's been a while since anybody really mentioned some of the PhD research that I did, because it's pretty disconnected from some of the stuff I do now. And I want to also thank John for the very kind introduction to speak to you all today. So it's a pleasure to be here. I do want to say I want to keep this very informal. I really welcome questions during the presentation, in addition to at the end. I guess since people online, maybe can't hear the questions, I'll do my best to repeat them, but remind me to if I forget. And then the other thing I'll say is, I know this is kind of a different audience, and I was trying to kind of calibrate the talk. So I see some of the people from Alp's group in the audience, and I see Alp in the audience. And so some of the early introductory material will maybe seem very basic to you, and but bear with me, and maybe it's good every once in a while to take a step back and think about some of these more basic things. But I wanted to make sure that this talk was also somewhat approachable for like someone with more of an engineering background and a practical sensing oriented background. So what I want to tell you about today is some of the work in my group on quantum sensing broadly, and I'll tell you a little bit about the work that we're doing in my group on quantum sensing with nitrogen vacancy centers in Diamond that actually has some connections to some of the work also going on in Alp's group, for example, in Alp's labs. And then I want to tell you about these ultra precise optical atomic clocks. I'll explain what that is and how they work, and then I'll tell you about how we're using them to do tests of relativity and measure some new things that haven't really been measured before. So here's the outline. As I said, I wanted to start kind of broad, just give you an overview perspective of what is quantum science and what is quantum sensing, and what are some of the maybe potential near-term impacts that are relevant more for engineering and industry-oriented people, as opposed to just physicists like us who just think some of this stuff is cool, but really what are the applications. And then I'll say a few words about quantum sensing, and in particular, a little bit about quantum sensing with these defects in Diamond called nitrogen vacancy centers. And then the last part of my talk will really focus on this testing relativity with an optical atomic clock. So what is quantum science? So quantum science is all about using the kind of strange and unusual aspects of quantum mechanics, the properties of quantum mechanics that we don't get in classical physics and sort of Newtonian classical physics that we're used to in the world around us is mostly classical, to do something interesting and to do something useful that otherwise we are not able to do. And so there's a few different weird and unusual aspects of quantum mechanics that we try to take advantage of when we're developing quantum technologies. And the first one of those is the quantum in quantum mechanics, which is just quantization, right? So it's just the fact that all different properties tend to be quantized when you're talking about quantum mechanics. So for example, energy is quantized. The orbitals of an electron are quantized. It can only be in certain states, and that's because it can only have certain well-defined energies and also certain well-defined angular momenta. And that then restricts where the electron can be and what state it can be in, and gives you these kind of nice orbital diagrams that we all remember from high school physics and chemistry courses and things like that. And of course, this is also responsible for atomic spectra and atomic transmission. So this is evidence. This is probably the simplest and easiest evidence you can find of quantum mechanics in the everyday world. Go look at the plasma discharge from any lamp that has an element in it. For example, neon. Right? Go look at a neon lamp through a diffraction grating. Put on little diffraction glasses, and you'll see all these individual well-defined lines that correspond to the energy level transitions between these quantized states of the electron around the nucleus, right? And the first point I want to make is, of course, that just that property, the fact that things are quantum and the basic properties of quantum mechanics itself, is already the basis for a number of important technologies that we actually take for granted and use and interact with in our everyday life, right? And the quintessential examples of this are atomic clocks and the GPS network. And many of us just use this in our cell phones on a daily basis to navigate. We no longer bother to learn how to get from one place to the other or figure out where we are at any point in time, because we can always just check on a map. And this is, of course, enabled by having these incredibly precise atomic clocks, which I'll explain how they work later in the talk, that allow us to actually locate exactly where we are in the position of the Earth by using the finite speed of light and the delay time between the signals that get to us from each of these satellites that have these atomic clocks inside of them, which is just mind-blowing, right? And we just totally take it for granted and forget about it. And of course, the laser is also kind of ubiquitous. It's unfortunate that now I use a digital laser pointer, so I can't make the point that I'm using a laser to give the talk. But we use lasers all over the place for telecommunications. Of course, on Zoom, my talk is being broadcast using a bunch of lasers that are sending this information rapidly from one point to another. NMR and MRI, all of these technologies, basically, primarily SQUIDs are maybe a little bit different, but the SQUID stands for superconducting quantum interference device. Those are a little bit more complicated and maybe use some of the other weird aspects of quantum mechanics that I'll get to. But these first three technologies, they really rely just on quantization. But the other thing about them is these generally involve many billions of atoms. These are really ensemble quantum technologies. And you could argue that some of the things, the behavior you see, you can kind of understand classically. I mean, it's at some point getting into semantics, but really we're not working with the individual quantum systems. And as a result, we don't see some of the kind of weirder behavior that we would predict from quantum mechanics. And so quantum science research today really focuses on, can we harness some of the other, even stranger properties of individual quantum systems, of well-isolated quantum systems and small numbers of quantum systems to do something, interesting and maybe have the kind of transformative impacts on society that some of these first generation quantum technologies have already had. So what are these kind of weirder aspects of quantum mechanics? One is superposition. So we just said that the electron around an atom can only be in very specific states, and that's true. But also, strangely, even though the electron can't be sort of in between these two states in terms of its energy, it can be in both states at the same time, right? And that's kind of a strange thing that's not familiar to us from our classical world that we live in, the idea that you can have these superpositions of multiple states. And not only in terms of energy, but also in terms of position. You can actually be in two places. Electrons can be in two places at the same time. And we know this is true even for fairly massive particles. This has now been measured for fairly large molecules and things like that, that they really are in spatial superpositions and have to be described by a quantum wave function. So that's a very weird aspect. And related to that, okay, for experts in the audience, if you have a qubit, a two-level system like this, you can generically write down, it can be in any combination of these two states, but you have to fulfill the requirement of sort of normalization, or probability has to be conserved. I'll get to that in 1 second. And what that means is that you require that these coefficients out front sum to 1, even though they can be complex numbers. So what that ends up meaning is that the state this two-level system can be in is described by the surface of a sphere, and that's known as the Bloch sphere. Okay, but so what's weird, and the reason that I bring up probability, is that measurement actually plays a role. And typically what happens is if you have one of these systems and it's in a combination of these two states, before measurement, it can be in any arbitrary superposition. But if I measure using the appropriate measurement operator so that I project into these states, I'll only ever observe it in either 0 or 1, right? And what this state actually describes are the probabilities that after the measurement, I'll measure either 0 with probability a squared or 1 with probability b squared, right? And therefore, for probability to be meaningful and to make sense, and for reality to make sense, we require that a squared plus b squared has to be equal to 1, right? And this is a weird thing as well. This is a weird aspect of quantum mechanics, that measurement somehow changes the state. After we've made the measurement, we're no longer in the superposition, but rather we're just in 0 or 1. And I would say this is one of the things that still troubles some people about quantum mechanics, is this kind of non-unitarity. You can't go backwards in time from the state of just being in 0 to the superposition. That's very strange, because we think stuff should be reversible in time in general. And then also the fact that there's some kind of weird kind of wave function collapse, which is related to that, is problematic. And then from a practical perspective, the fact that these measurements are non-deterministic and are probabilistic is something that we kind of always have to deal with when we're working with quantum technology. So whether you're working on a quantum sensor or a quantum computer, the fact that the outcome is fundamentally non-deterministic puts limits on the performance of that computer, and also informs how you design a sensor or computer that actually works and does something useful. And related to that is a kind of important principle of quantum mechanics that's also somewhat strange to us from a classical perspective, which is that you cannot copy a quantum state, right? So there's something called the no cloning theorem, and it might not bother you that you have this non-deterministic nature of this, because if you could just make copies of the state, you could just perform the measurement an infinite number of times and learn exactly what state the particle was in. But in fact, quantum mechanics says, no, you can't do that. You're left with exactly one of these states to work with, and you never learn everything about the state. And that's sort of also a problem for us when we're designing sensors with these systems. Okay, and then the last weird, and arguably by far the weirdest aspect of quantum mechanics, if all that stuff wasn't weird enough, is the concept of entanglement. And here the idea is, suppose I put one of these atoms or electrons around an atom in a superposition of two states, but the other one is just in a sort of more classical single state, the zero state here. And then I do a logical or conditional gate, just like we're used to from classical computing. And I say I'm going to flip the state of this atom conditional on what state this is in. But if I do that in a way that's sort of coherent quantum mechanically, then if this initial atom was in a superposition, now the outcome of this conditional gate is also sort of in a superposition, is in a combination of two different states. And if you look at this state, it's a very strange state where now with probability a squared, both atoms are in 0, and with probability b squared, both atoms are in 1. And that's very strange, right? Because now the states of these atoms are fundamentally intertwined with each other, and you can no longer separate out the state of one atom or the other atom. You have to talk about them together. And even weirder, I can take those atoms and keep one of them here and in Quarry Hall and take the other one to Australia, let's say, and that still has to be true. And if I do even an operation on one of these atoms, it somehow will seemingly instantaneously impact the state of the atom on the other side of the world. And that's a very kind of weird and troubling thing. It really bothered Einstein, for example, because it seems like it might violate things like causality, and things seem to be traveling faster than the speed of light. It turns out that you can't use this to communicate faster than the speed of light or to violate causality. And what preserves those things is that randomness of the outcome of your measurement. So the fact that if I only make a measurement on one of these two atoms, I just measure either 0 or 1, I can't really figure out what was being done to the other atom. But later, when I communicate classically, I'll actually see that they still have these correlations, and all those correlations were preserved. And that's the basis of this principle, this thing called Bell's inequality violations, which, as I mentioned a minute, was the subject of a recent Nobel Prize, and much of the research was done, initial research was done by John Clauser here at Berkeley. So, these are all very weird properties, and what we try to do is figure out to what extent we can actually take advantage of them and also combat some of their negative aspects to make kind of interesting, technologies. Very quickly, I just want to mention, because it's kind of famous and everybody knows about it, the Schrodinger's cat, this kind of unfortunately macabre thought experiment that Schrodinger came up with, where the idea is that you have a cat in a sealed box, and you have some kind of radioactive decay, and you have a detector that detects whether the particle has decayed or not. And if it has decayed, it smashes the poison capsule and murders the cat. And so the argument is that because that's a kind of quantum process, the atom will be in a superposition of having, or nucleus will be in a superposition of having decayed and not decayed. And if you wait to exactly the half-life, that means that if this cat is in a perfectly sealed box, from our perspective outside, the cat is in a superposition of being alive and dead, right? And that's a sort of very weird and ridiculous thing. We don't know how to do this, mostly because we don't know how to make a perfectly sealed box that isolates information so that we can have no way of knowing independently whether this particle is decayed or whether this thing is smashed and all this kind of stuff. But what's interesting is that when people were thinking about this and coming up with this thought experiment, they kind of drew the wrong conclusions. And in particular, Schrodinger himself explain this away by saying, we never experiment with just one electron or atom or small molecule in thought experiments. We sometimes assume that we do, and this invariably entails ridiculous consequences. So his explanation was, oh, don't worry about it. I'm just realizing that maybe, does this change anything if I do that? Yes, okay, sorry. Should have done that from the beginning. Hopefully you guys didn't miss anything. Okay, so his conclusion was, it's okay, this is all thought experiments. We can't actually do these experiments, so it doesn't matter. Yeah, the math is weird and it makes weird predictions, but it's fine because we never get to do these experiments anyway. And of course, we don't do experiments, fortunately, where we murder cats. but we do these experiments with small numbers of atoms and molecules and electrons now, right? And in fact, he drew the wrong conclusion. You can see all of this very weird behavior in the lab, and in Alp's lab and my lab. We see these kinds of things on a daily basis, and that's really pretty amazing. And so the sort of history has been over the past 40 years or so, we've developed all these different platforms where we now have these isolated, yes, shoot. Yeah. Here?
Yeah. Why is the state always like either 0011 when NB01?
Yes, great question. It can. So what I did is I set up the problem in a way where I started out with one qubit being in 0 and 1, and then I did a very specific logical operation that left us in this particular state. But more generically, you are absolutely right that there should be 4 numbers now that describe the complete state. I just, kind of left those out. And actually, when I give this talk and talk more about quantum computing, which I'm not going to do, I go into that and show this kind of exponential Hilbert space and things like that. But yeah, great question. Excellent. The last 40 years or so, we have all these different isolated quantum systems that we can now see these kinds of weird quantum effects in, and we can try to harness them to do interesting stuff, right? This has been the subject of a couple of Nobel Prizes relatively recently. In 2012, Saoirse Roche and Dave Wineland both got the Nobel Prize for work on experiments in individual or isolated quantum systems. And then much more recently, as I mentioned just a couple of years ago, Elena Spey, John Clauser, and Anton Zeilinger won the Nobel Prize for these measurements of Bell's inequalities, proving that entanglement is real and that, at least under a certain set of very reasonable assumptions, quantum mechanics is truly a non-local theory. So, meaning that these particles really are fundamentally intertwined no matter how far apart they are, and somehow seemingly something seems to be sort of non-local or be transmitted instantaneously between one and the other, right? Which is very strange. I'm showing you this both to convince you that this is real stuff and is now kind of established to the point where it was the subject of a Nobel Prize, and also just to remind you of a simpler time when the Nobel Prize in physics was actually awarded for physics research and not for artificial intelligence. But anyway. So then quantum science is the idea that we want to harness this weirdness to do interesting stuff. And in particular, so far, I think we've come up with kind of 3, and by we, I don't mean me, but the entire field. It wasn't me who came up with any of these ideas, have come up with the idea that there's kind of 3 different things that we can in principle do with these technologies. The first is we can build a quantum computer or a quantum simulator and use the weird aspects of quantum mechanics to solve problems that are fundamentally intractable or hard on computers. So either solve problems that are impossible on classical computers, all the computers that we have today, or maybe solve them faster in certain cases. But I think most people agree that it's so hard to build a quantum computer that you should probably mostly focus on the problems that you actually just fundamentally can't solve on classical computers. Okay, the second sort of use case is quantum sensing, which is use the well-controlled quantum systems and some of these weird things like entanglement that we have in superposition to detect weak signals with higher performance, where performance could mean any number of different figures of merit. It might mean that our sensor has higher sensitivity. It might mean that it has better spatial resolution or spectral resolution. It might give you more bandwidth or dynamic range. There's any number of things that we might care about that in principle, by taking advantage of some of these kind of properties of quantum mechanics, or arguably just being aware of them and use it, taking advantage of ways to kind of use their push to the ultimate limits enabled by quantum mechanics, and engineer so that we kind of bypass some of those limits to some extent, we can improve these figures of merit. And then the last technology that we've come up with is quantum communication, which allows us to basically communicate privately by sending information using quantum bits. And this offers sort of physical verification or physical certainty that nobody was able to see the bits that you use to distribute a secret key that you then use as a cipher to communicate, provably securely. And so those are kind of the 3 technologies that we call quantum technologies that we're working on today. And this is kind of my own take, my own interpretation on kind of what the short-term and long-term potential impacts and use cases of these different technologies are, kind of more from an industry perspective. This is just my own take. It's not probably comprehensive, and it's somewhat biased. And one way you can tell it's biased is I mostly work on quantum sensing, and most of the stuff on the list, and especially in the near term, is focused on quantum sensing. But I personally believe that's also kind of a reflection of reality to some extent, which is that the technology, when we talk about these technologies, that's probably most mature and closest to real world impact right now really is quantum sensing. Longer term, some of these other technologies really could have truly transformative impacts, but in the near term, it's a little bit less clear what quantum computing and quantum communication is really useful for right now. So I want to focus the rest of my talk really on this middle one, quantum sensing, and tell you a little bit about a couple different examples of it. And so, in the near term, quantum sensors really could be used and are starting to be used for things like mineral exploration, medicine and drug development and biophysics experiments and things. In principle, I think navigation and transportation is a big one. People really want to use these kind of technologies for GPS-denied navigation and inertial navigation. And also potentially for things like security, just things like metal detectors or detecting bombs and things like that. And then arguably also for things like process control for nanofab and things like that for the semiconductor industry. Longer term, you can imagine that maybe some of these technologies that right now are really space age, science fiction type technologies, very hard to build, very expensive. Maybe one day we can shrink some of these things down and start to put them in household devices and mobile devices and autonomous vehicles and things like that. And I think that's maybe not even that far away from reality. Okay, so what's the idea behind quantum sensing? I already told you. And here are some examples of different kinds of quantum sensors that you can build. And the one that so far has truly demonstrated that you can measure something that you otherwise cannot measure without using some really weird aspects of quantum mechanics is LIGO, the Laser Interferometer Gravitational Wave Observatory. This is, a kind of very special telescope that physicists have built to detect gravitational waves from binary black hole and binary neutron star mergers, very far out in space. And they detect these very minuscule ripples in space-time caused by these cataclysmic events that are happening many millions or billions of light years away. And remarkably, most of the events that are observed, and we're at the point now where these observatory, there's 3 of these things that are operating, but they really form one observatory together. There's 2 of them in the United States, one in Louisiana, one in Washington State, and then there's one Virgo in Japan. Sorry, I think Cogra is in Japan. I think Virgo's in Italy. Yes. Sorry, in Italy. Yes. Yeah. So there's also Cogra that I think is somewhat contributing. So Cogra in Japan and Virgo in Italy. And these things combined form one detector that can see these events. And these events occur roughly at a rate of a few a week. They're now seeing them. And most of those are only enabled because they're using non-classical states of light. They're using squeezed light in these interferometers. And otherwise, they would be below their noise floor and not able to observe them, right? So this is the one example where we're really seeing signals and learning about the universe using technologies that just would not be possible without real quantum sensing techniques. And then there are these other examples of atom interferometers, nanoscale sensing with NV centers, that I'll talk about in a minute, trace gas detection, for example, and ultra-precise atomic clocks. So to dive in on one of these examples quickly that I work on myself, I'll tell you a little bit about the idea of nanoscale quantum sensing. And the system I work with to try to make nanoscale sensors are these defects in diamond known as nitrogen vacancy centers. These are naturally occurring defects that happen inside of a diamond lattice. So diamond is made up of carbon atoms, and you can replace one of the carbons with a nitrogen, and another carbon is just missing. That's what's called a vacancy. And if those two happen to be sitting on neighboring sites, then you get this defect known as a nitrogen vacancy center. And it so happens that it's in one particular charge state of this defect, its level structure is particularly easy to work with, and it really behaves like an atom or molecule trapped inside of the diamond that we can use to measure local properties like the local magnetic field or the local temperature using these defects. And what's nice is we can really isolate single ones of these defects. Each of these bright spots here is a single nitrogen vacancy center in the diamond. And just by doing basic spectroscopy, using really basic tools like a single laser, a single microwave source, and something that collects and counts the photons that come back, you can measure what's the magnetic field, for example, at the location of this defect and along a specific axis. And so this is appealing because it's both, if you use multiple defects, you can use this as a kind of vector magnetometer, but also it's really telling you about the magnetic field at a point that's really very well defined. And because you're trapped inside of the diamond, these can be just a few nanometers below the surface and still maintain most of their properties. And so you can now really measure magnetic fields at a new length scale. And there's this nice plot from a book about magnetometry that shows that the NV center is really kind of sitting on its own here in terms of spatial resolution. It's not the most sensitive magnetometer, but it is kind of off on its own compared to all other magnetometer technologies in terms of its combination of sensitivity and spatial resolution, right? And this is really what we want to take advantage of and what makes the NV special and why we say, okay, we want to do quantum sensing with these NV centers, for nanoscale sensing. So this has led to a bunch of different sensing modalities that people are pushing forwards with these defects, and also sort of sensing targets. And a few examples of that are things like doing single protein NMR style experiments where you really try to sense single nuclei within a neighboring protein and maybe learn about the structure and dynamics of that protein, even in solution and while that protein is folding and things like that, which is not something that's currently possible. The way that we learn about most protein structure these days is by doing X-ray crystallography or cryo-EM, and in both cases you have to sort of freeze that protein in place. It can be somewhat destructive and it's hard to see dynamics that way. And you measure bulk properties. Typically you measure many proteins to learn about what one looks like. Here, in principle, at least, the dream is we can really study a single protein as it undergoes dynamics in a relevant environment. And that's a kind of new thing that we think these quantum sensors can enable. Another example is to make kind of scanning probes like AFM or MFM, but where you have one of these NV centers at the point of a tip, in a tip very close to a sample, and you can really scan it over an interesting condensed matter system and try to learn about things at the nanoscale, image ferromagnet or anti-ferromagnetic domains that you couldn't otherwise see with some of these other measuring technologies. Just to give one example that's maybe relevant for industry and for some of the things that are going on here at bsac and in this building, people are trying and arguing that you might be able to use these to look at kind of currents inside of integrated circuits. You can also use them as thermometers. So you might also be able to measure heating and temperature inside of integrated circuits and at scales that you otherwise maybe can't access. And the argument of this particular paper was that maybe you can learn this to use this to learn about kind of what's happening inside of stacks that you otherwise maybe couldn't have access to, and maybe learn about things like leakage currents and things like that. And just to make a connection to some of the work going on by some of the people in the audience and going on here, you can imagine an even crazier idea of maybe actually using defects that Alp and his group are pioneering and doing the same kind of sensing inside of the chip using defects that are just naturally there in silicon, right? So because of all the great work that's being done by Alp, and his collaborators and colleagues, we now have quite a bit of control over defects that occur inside of silicon itself. And so you can imagine maybe someday using them to do some of the same sensing and learning about what's happening inside of an integrated circuit. But one point I want to make, and to tell you a little bit very quickly about what my own group is doing, all the experiments that we do with these defects right now, we tend to work with one defect at a time or ensembles of many billions of these defects. And I would argue that because the primary advantage of these defects is the spatial resolution that they offer, you really do want to do experiments with individual defects. That's part of what really makes them unique. But the technology that most people use to work with these defects is called a confocal microscope. And when you see an image like this, actually this image is made by scanning one point at a time and collecting information pixel by pixel. And what that means is that you really can only work with one of these defects at a time. And what we've done in my group very recently, and this is published on the archive just a matter of a month or two ago, or it's posted on the archive a month ago, and it's under review right now, is develop a new platform inspired by a lot of the work going on in experimental atomic physics right now that enables us to work with multiple individual NV centers in parallel and simultaneously. And so here, this is an example of doing single NV center measurements with 10 NV centers all at once and collecting all this information in parallel. And that allows us to do fun things like make movies where you can actually see these individual single atom scale defects light up as we hit the resonance for that particular defect. So this is a kind of really telling you about the magnetic field locally at each of these locations in space, but all in parallel simultaneously. And we've since, even this was posted, this is not in the paper that's posted in the archive, we've scaled this up now to hundreds of these defects. And I don't really see any reason why we can't go to thousands. And this is really kind of a new platform that I think will enable some of the promise of these individual NV-centered defects. So that's just an ad about some of the other work going on in my group. So in the last part of my talk, I want to tell you a little bit about these ultra precise atomic clocks that we also work on. This is sort of building on that first generation technology that I already mentioned, which is that atomic clocks are one of the quintessential first generation quantum technologies that has really changed the world and that we use on a regular basis. And now we're using some of our better control and better isolation of these quantum systems to make even better atomic clocks and develop new applications. So what is a clock and what is an atomic clock? You know, I probably don't have to tell any of you this slide you all probably know more about than I do, right? A clock is something that exhibits a periodic phenomena that we can count. And in particular, you know, a simple harmonic oscillator is kind of the best sort of thing for that. It has a well-defined frequency, and so therefore it has a well-defined period, and you just count the periods of that simple harmonic oscillator and you use it to keep track of time. And so inside of all of our cell phones and laptops and everything, we have these little piezoelectric quartz tuning forks. You know, they tend to pick a frequency that's nicely dividable so that you can, in the end, convert this ticking into the passage of seconds that you display, or minutes in this case, that you display on a watch hand or whatever, a digital clock. And that's a clock, that's a local oscillator. The problem, as I'm sure you're all aware, is that every single one of these local oscillators that we make, every single one of these quartz tuning forks is slightly different. There's always imperfections in the manufacturing. It's a man-made object, so every single one will be slightly different from every other one. And then in addition, they're kind of imperfect things. Quartz ages, it turns out. So if you look at the frequency of these tuning forks over time, there's kind of a very characteristic trend that you always see. In addition, if the temperature changes because of the coefficient of thermal expansion of the material, the shape or the size of the tuning fork changes, and that changes the frequency. So as a result, these standard ones that we have in our phones or in our microwave ovens and things like that are usually precise to something like 3 seconds in a month or so, which is fine for a clock that's only showing you minutes, you know, like on your microwave oven, but isn't so great for physics and and is certainly not good enough for something like GPS to work, right? But it also gives us a kind of figure of merit that we can use to figure out how good these clocks are. In particular, we just take this 3 seconds and divide by the number of seconds in a month, and we get a unitless number that tells us kind of roughly how good this clock is. And our goal is to get that number as small as possible, because that means it'll take more seconds for it to get off by a second, basically, right? And so the way to do that is to introduce the atom into the atomic clock. And this is serving as a frequency reference. So again, we take advantage of the quantization of the energy levels inside atoms, and the fact that all atoms are of the same element are basically identical, especially if you prepare them in the same state and in the same environment. And so what we can do is we can take the frequency of our local oscillator, multiply it up a bunch of times, and then compare it to a transition inside of an atom, such as the hyperfine transition of cesium, and check if it's on resonance or not by counting how many atoms get excited from the ground state to the excited state. And if you're on resonance, they should all get excited. And if you're off resonance, very far off resonance, none of them should get excited. And in the middle, you can sit here on the edge of this transition and use that to feed back and correct for the drifts of your local oscillator by seeing changes in the number of atoms that get excited up or down, right? And this works very well. So as I mentioned already, this is the basis of GPS, and it's just cesium and rubidium clocks in these satellites that enable the GPS network. It's also, we've gotten so good at making these clocks that they're now the best measurement devices that we can make that measure something with units. And so we now define all SI units in the new SI that was adopted a few years back. We now define all SI units with respect to a bunch of fundamental constants, which are just numbers that we write down, and the hyperfine transition of cesium. And what that means now is that our ability to measure anything with units is actually limited by our ability to make good clocks. Yes?
So for rubidium clocks, there's this kind of nice convenience that you can basically convert to a lamp. So
yes.
They're not dirt cheap, but relatively cheap.
Yeah.
For cesium clocks, what's the complexity?
Yeah, so it turns out that they've found ways to kind of do similar things with cesium. It's not as nice that you have this nice coincidence with the isotopes and you only have one isotope of cesium. And I actually don't remember the details of exactly how that works, but they also managed to make it work, basically. Yes, correct. Yes, so you can also make vapor cesium clocks that work with a lamp. And these the satellites have both in the cesium and rubidium clocks. But actually, I don't remember the details of how they do that. It's a good question. So this kind of motivates the fact that, first of all, we would like to make GPS a bit more robust and reliable. It turns out that the level of performance of these clocks currently in GPS requires that they be corrected for their relative drifts every few hours or so. And so we'd like to actually bring that, down so that you only have to correct them every few days or every few months or something like that. So we'd like better clocks in these GPS satellites, but also we'd like to be able to measure things, more and more precisely and so improve our ability to define things with units at all. And that really motivates kind of continuing to work on better clocks. And you can see that there's been a tremendous amount of performance, progress, and there's kind of a Moore's law-like scaling for the performance of these clocks in terms of this fractional frequency uncertainty that I already introduced to you. The quartz oscillator that I showed you had something like 10 to the minus 6. Now clocks today are reaching, the very best clocks like the ones I work on are reaching fractional frequency uncertainties at the 10 to the minus 18 level. And part of what's enabled that is moving from these microwave transitions, these hyperfine transitions in atoms that are hydrogen-like, like hydrogen, rubidium, or cesium, moving to optical transitions in slightly more complicated atoms like strontium. And by moving from a microwave to optical transition, this basically just means that you can count more oscillations per second, everything else being equal, and therefore make a better clock. And as a result, you can see that actually microwave clocks were kind of slowing down in terms of their improvement. And then with the introduction of these optical clocks, we've continued to improve at even arguably a faster rate than the microwave clocks were improving at. And we've now reached this level of accuracy of 10 to the minus 18 that corresponds to 1 second or below 1 second in 14 billion years, right? So if you kept two of these clocks taking side by side from the Big Bang until now, they'd agree on the age of the universe to better than 1 second, which is really pretty amazing. So, and so you can ask, well, that seems a little stupid, right? Like, do you actually need clocks that good, right? Another comment I'll make that people often get confused by, I'm sure you all appreciate it, but that's not to say it's easy to make a clock that runs for 14 billion years. It's hard to make these clocks run for an hour at a time, let alone 14 billion years. But rather, this is a way to understand just how accurate and precise they are, right? Yes? Yeah, that's an excellent question. That's at the 10 to the 4, 10 to the 5 seconds. You average down for something like 10 to the 3, 10 to the 4, 10 to the 5, you get down to this 10 to the minus 18 level. And I'll come back to that point. It's a very good point. But this has been demonstrated, and that really is the level that has been measured in clock comparisons, but after averaging for an hour or something like that, or even more. Okay, but you can ask, all right, do we really need clocks this good, and what else is this good for? And this is really my primary area of research and interest, which is developing the novel applications, kind of harnessing this new precision that's been unlocked by this new technology and finding new ways to use it. And in particular, we want to use it to search for new physics, do things like look whether constants are varying in time or space, fundamental constants of nature, but also map Earth's gravity, maybe try to detect dark matter with it, maybe try to do some of the same kind of stuff that LIGO is doing. These numbers start to kind of approach the kind of numbers that LIGO is demonstrating. And then also, I really like to do kind of fun tests of relativity, which is a natural thing to do with these clocks, and to see some of the weird aspects of relativity in the lab, just like we can see some of the weird aspects of quantum mechanics. We don't normally get access to relativity in the lab, but these clocks let us do it. So the very last part of my talk, I know I don't have too much time left, I want to tell you about one example of that. So in particular, I want to tell you about measuring an effect of relativity. It's a non-classical effect, it doesn't come out of Newtonian classical mechanics, called the gravitational redshift or gravitational time dilation. And the idea here is that basically because of Earth's gravity, if you raise a clock up with respect to another clock on the surface of the Earth, the higher clock will tick faster than the lower clock. Because this is a relativistic effect, it's a very small effect. The effect scales with the acceleration due to gravity on the surface of the Earth, little g, the height difference between the clocks, and then divided by c squared. And because the speed of light, c squared is a big number, this is a small number. You can plug it in, g is 10. So if you plug in 1 meter and 10 there and 3 times 10 to the 8, it works out to be almost exactly 1 times 10 to the minus 16. So at 1 meter height difference, these clocks tick at a difference of a part in 10 to the 16. And it's a very, very small effect, but these clocks are very good, so we can measure it. I'll just mention that this was a major plot point in the movie Interstellar. In that movie, they were near a black hole, so the effect was significantly stronger. But it's not science fiction, it's actually real. And in particular, in the 1960s, Pound and Rebka did this pioneering experiment with Mossbauer spectroscopy, where they showed that they could actually see this for clocks separated in height by about 20 meters or so. And that was the first experimental measurement of this effect. Since then, we've gotten better clocks. And in a beautiful experiment in 2010 at NIST in Boulder, they showed that by raising one clock up by a foot with respect to the other clock, they could actually see this effect show up just barely at the sort of foot level. And now the clocks have gotten so good that in principle, we should be sensitive to these effects at kind of a 1 centimeter height difference level, right? Which is cool, but also actually a big problem for these clocks, because it means that if you want to do comparisons between clocks at different standards institutes, you need to know the relative heights of those clocks to the centimeter level with respect to Earth's gravitational equipotential. And we actually don't know that for, institutes separated by more than a kilometer or so. We have no way of knowing what those equipotentials kind of really look like. And as a result, you actually can't compare these clocks at the level that we can make them anymore between different standards institutes. So you either have to build them side by side, which is something these standards institutes are doing, or you have to find some other way around this. And one thing is, just like in everything in Silicon Valley here, it can either be a feature or it can be a bug, right? And so you can turn this bug into a feature by using clocks now to measure Earth's gravity, turning it around on its head and saying, if I can make these clocks portable and move them around and put them at different nodes of an optical fiber network, for example, I can actually use this to make better measurements of Earth's equipotential and Earth's gravitational potential than I can any other way. So people are starting to do these kinds of experiments. And I'm really interested in that as an application, but also just in the idea that you can measure these kind of relativistic effects. And also I want to push on the performance of these clocks and get even further. And in particular, if you want to use these things to do gravitational wave detection and things like that, you actually need to do quite a bit better even than this 10 to the minus 18. It's already a very impressive 1 second in 14 billion years. If you want to compete with LIGO, you have to actually have numbers in terms of fractional frequency uncertainty that are comparable to LIGO's fractional strain uncertainty. And that corresponds to numbers of the 10 to the minus 21, 22, even LIGO achieves 10 to the minus 23 per root hertz, which is truly staggering, okay? But if we're interested in looking at a different frequency band, we should be able to see interesting stuff at the kind of 10 to the minus 20 per root hertz-ish level. So that's a long way away. And as you pointed out in your excellent question, very insightful question, this is not 10 to the minus 18 per root hertz. This is after averaging down, right? And so we have a long way to go to maybe do some of the things I want to do with these clocks. So we built a clock to kind of move in this direction. We built an experiment to give you some sense of what it looks like. It's a room scale experiment. It covers 3 fairly large optical tables with optics and lasers, has something like 12 different lasers in it. And in the end, what we achieve is laser cooling of a cloud of strontium atoms. That's this glowing blue ball here. I'll show it to you in another picture here. Laser cooling of strontium atoms and then optical trapping of these strontium atoms in an optical lattice at about a millionth of a degree above absolute zero. So 1 microkelvin or even less temperatures inside of a very good vacuum chamber. And then we compare our local oscillator, which no longer is a little quartz tuning fork, but is now high finesse optical cavity made of ultra low expansion glass, ULE. That serves as our local oscillator. We lock a laser to this thing, and then we compare the frequency of this thing to our atoms on this beautiful clock transition that is provided to us by nature for strontium. And this transition has 400 terahertz frequency and a 1 millihertz line width. So as Alp mentioned, this is a natural quality factor of this transition provided to us by nature, about 10 to the 18. Okay, and we want to take advantage of that. But the problem actually is that our local oscillator has a much worse quality factor than that. It's still pretty good, but it's more like a hertz level as opposed to a millihertz. So rather than being a 10 to the 18, it's about 10 to the 15. And that kind of limits the performance of our clock. So in particular, when we actually run as a clock, we get a performance of something like 6 times 10 to minus 15 per square root hertz. That's a pretty good clock. It's not the best clock. There's the best ones are about an order of magnitude in terms of stability better, but still it's pretty good. But then you can say, how long would it take you to get to 10 to the minus 20? And you'd have to average down for 11,000 years at that stability to get to 10 to the minus 20. And that's too long even for a PhD, right? And so, and this is only one measurement. It would be one measurement at 10 to the minus 20. So we need something else. And of course we saw that coming. So we built our apparatus with this in mind, and we built something kind of special. Rather than just loading one ensemble of strontium atoms, we load multiple ensembles of strontium atoms into our optical lattice, and we do differential comparisons between them. And at least for certain things, like doing tests of relativity, or ultimately for doing things like looking for gravitational waves or dark matter, it turns out we don't care about the absolute frequencies of these clocks. We always want to do comparisons between them. And this is a platform that enables us to do these comparisons while getting rid of a lot of the limitations that typically limit the performance of your clock. And in particular, the biggest one is actually the noise of the local oscillator itself. When we do a differential comparison between these 2 ensembles, we can make that common mode and kind of cancel it out. And that works extremely well. So what we show in this paper is that we can go from this 100 milliseconds of kind of coherence time when we compare the atoms to the light to 26 seconds when we do a differential comparison between the two atoms. We've since pushed that out to 75 seconds, and now even past 100 seconds or so. And now we're at 100 seconds, we're really starting to take full advantage of this millihertz line width transition and reach these quality factors of 10 to the 18, as Alp alluded to. And this gives us stabilities for the differential comparisons between these clocks that are about 3 orders of magnitude better than what you get from the single clock performance. And then that's in stability, so it's per root hertz. So that gives you 10 to the 6 enhancement in how long it takes you to average down to a certain number. And so now, rather than taking 11,000 years to get down to 10 minus 20, it would take 6 days to average down to 10 minus 20. And that starts to become reasonable. We still have more work to do. We want to get to like 10 to minus 20 per root hertz. And I think there's kind of a clear pathway to doing that using some of the techniques that we've demonstrated here. So we can also load more than just 2 regions. We don't have to stop at 2. And so this is showing that we can load 6 of these regions using the same kind of approach. I'm skipping over a lot of details about how this works. Feel free to ask if you want. But now we can load kind of a network of clocks and do intercomparisons between this network kind of all in parallel. And this is very similar and actually inspired some of the work I already told you about with NV centers. It was inspired by some of the stuff we were doing with these clocks. Okay, for reasons that I won't go into, each measurement when you do a differential comparison gives you one of these nice ellipses that we fit to. So when you have 5 clocks, as we do here, and you do 5 choose 2 differential comparisons, that gives you 10 ellipses or 10 measurements of the frequency differences all simultaneously. And this is kind of perfect for doing a test of this gravitational redshift, because as you can see, all these clocks are at different heights with respect to each other. We align this kind of array of clocks vertically, and we have differences in height here of 0.25 centimeters or 2.5 millimeters, and then a total difference between this clock and that clock up there of 1 centimeter. And that means that we can now test the redshift or try to measure the redshift for clocks separated by 1 centimeter between this one and this one, but also for 4 different pairs of clocks that are separated by 2.5 millimeters all simultaneously, right? And then if you look at the numbers, for 2.5 millimeters, that's a change in frequency of these clocks of something like 2.75 times 10 to the minus 19. And for our stabilities that I just showed you, that means you only have to average for about 30 minutes before you should be able to see the gravitational redshift start to show up here, average down to really resolve it. But that's only the statistical uncertainty. That's really only sort of just averaging down. You also have to worry about something else that can give you frequency difference between these clocks. That's not the gravitational redshift. So you have to worry about systematic uncertainties. And so we had to characterize all the other things that could give us frequency differences between these clocks in this array. There's kind of a laundry list of them. These are very well understood because these are the same things that limit the accuracy of the clocks that you make when you make, atomic clocks. And we characterized all these things. It was a lot of work. That's most of the work that goes into this, is actually doing this. And we actually did all that blind so that we wouldn't be biased in our measurement. And finally, when we unblinded our measurement and put together our systematics table and everything, we found that indeed, we really do see this effect. You can see that the fractional frequency gradient across this array of clocks is not 0. So the clocks, once you account for all the other things that we can think of, the clocks really are ticking at different rates. And the rate that we measure in terms of their height differences is this red line, and the black line is what you'd expect from relativity. So we're really seeing it. But even cooler, I think, is to visualize it this way and say, what does that frequency difference look like between these clocks as a function of height difference? And you can actually see the redshift manifesting itself across this array, right? And you can see that we can actually even resolve, in principle, frequency differences that correspond to a height difference of only about 1 millimeter or 1.5 millimeters. So we're now really seeing, the gravitational redshift show off at the thickness of a penny or so. And so what this means is that, if you have a penny sitting on your desk, the top of the penny is aging slightly faster than the bottom part of the penny. And if that bothers you, just flip them over every now and then. Okay. So I think there's a lot of cool directions that we want to take this in and that we're currently exploring for taking this kind of technology. That includes using the fact that we have multiple ensembles to make better absolute clocks, not just differential measurements, but really actually improve the overall performance of the clock by breaking up the atoms into multiple ensembles and more efficiently distributing and using the kind of resources that you have available. But also things, as I said, like pushing forwards on gravitational wave detection, doing even other kind of more exotic tests of relativity, and these kind of things. And so with that, I just want to thank my group, all the people who did all the research, and all the funding agencies that supported it. I want to especially highlight the people who did the clock work that I told you about, And in particular, Xin Zhang and Jack Doldy both came with me from Wisconsin and are now here at Berkeley. And you're welcome. Please, anybody who's interested, let me know if you want a lab tour and things like that. We're still in the process of rebuilding this experiment after moving it here from Wisconsin, in the very early stages, I would say. But we hope to have this up and running again in a matter of some number of months, 6 months, let's say, or something. And with that, I'll just thank you for your attention and take questions.
Okay, we have time for a couple of questions.
Yeah.
Is there a similar thing for time sensitivity?
Okay, so the question was, is there a comparable Planck time like there is a Planck length? And the answer is yes. We are many, many orders of magnitude away from it. It's at the sort of 10 to the minus 30 something seconds or something like that. And it's also not entirely clear to me that that maps directly into the numbers that we're talking about here, where you're talking about precision or accuracy of keeping track of some very macroscopic number of seconds. So it's an interesting question what that means and whether it puts fundamental limits on how accurate a clock can be. There are, I think, very fundamental limits on how good a clock can be. I'm not sure they're exactly set by this Planck length, but it's a really interesting question. Yeah. And we would love to get to the point where we become limited by that kind of physics, but we're very far away from it for sure, no matter what. It's a great question.
Any other questions? I have one quick one related to gas sensing. So obviously they would be very sensitive, these sensors, quantum sensors. But what about the selectivity? How do they make these, precise gas sensors be selective to whatever?
Yeah, that's a great question. I mean, there's a number of different ways that you can do trace gas detection. The one that I was showing you there are the ones I'm kind of more familiar with, which is using things like optical frequency combs to do cavity enhanced spectroscopy of a number of different optical lines simultaneously inside of a cavity. And those are all ways to increase your sensitivity, and measure very small numbers of molecules. But as you're saying, then the question is how to be selective. You look for, the very specific fingerprint or vibrational spectra, usually, of these very specific molecules, because they all have all the different vibrational modes associated with their different bonds. And you can make some kind of catalog where you try to match the spectra that you see with the fingerprint that you associate with a very specific complex molecule. This is active, areas of active research, but it really can work. And they can, in these kinds of experiments, see very small concentrations and positively identify that there are very specific molecules inside of there. And even now people are starting to do things like do breath analysis with these kinds of tools and see if they can use machine learning, because there it gets much more complicated. You have huge numbers of different kinds of biomolecules and proteins and everything, but they try to use machine learning to basically say, what does the information that I get out of this tell me about whether someone has a cold or COVID or something like that? And at least they show that there are correlations that they can really do better than dumb luck in guessing whether someone is sick. But whether or not it's at the level that is useful for making a new kind of COVID test that would be just a breathing into a tube or something, it's not there yet, but that's the kind of the dream work. One day, supposedly certain dogs can tell if someone has cancer or Parkinson's disease. The hope is that you can make a version of a dog's nose using the same kinds of techniques and one day see that. And I think it's a really exciting area of research, but it's still nascent.
Any other questions?
So it sounds like for a lot of these applications, you're a bit more counting on shorter frequencies rather than
Yeah.
So the better clocks that are are those the same clocks that are?
That's a great question. So, and it gets at something I kind of swept under the rug, which is that when we use this one number to talk about, fractional frequency uncertainty, we're wrapping up a bunch of different numbers in it, including sort of stability, precision, and accuracy. And some of the clocks can be very accurate without being very stable. An example of that is the single ion optical clocks, where your frequency reference is really one ion. And the challenge there is that you only get one bit of information every time you measure. And so it really then takes a long time to average down, but you can be incredibly accurate because you have this one ion that's very well isolated, that's really sitting on its own, and you understand extremely well, kind of its environment and what state it's in and things like that. And so it really depends on the application. I would say most of the time you care about a combination of these things, and we really do want everything, right? We want very accurate, but also we want to be able to average down very quickly. And so what that requires is having a lot of atoms. And then there's a trade-off there, because now those atoms start to interact with each other. You don't know as much about their states. It's a less well-controlled kind of situation. So the name of the game here is kind of how many atoms can you cram in there while still very well controlling their states and their environments. And that's a lot of what we do, is try to engineer that.
Okay, let's thank our speaker again.